So in this problem, we're doing retrosynthesis. So we're being tasked with, here's the molecule, and we want to know where it came from. And in this case, they're actually giving us a little bit more of a lead. They say we want to use Grignard reagents. Right? So we're going to use Grignard reagents. So if we see we hear about Grignard reagents, we should remember one of the first ways we learned how to use Grignards was to make alcohols by having Grignards react with carbonyls. So if I number these carbons, 1, 2, 3, 4, 5, like so, we can look and kind of get an idea for where the action's taking place. Right? So if we look at this, we should recognize that carbon 4 is really the carbon that has the electronegative atom on it, right? The oxygen. So the chemistry must have been going on there. And we've done this before where we thought about, well, if this carbon would be the electrophile, right? Because it's the one attached to the electronegative atom, right? It's delta plus because it's attached to oxygen. That means carbon 3 would have to be a nucleophile if we broke this bond, right? Every bond we make, somebody was a nucleophile, somebody was an electrophile. Somebody had electrons, somebody wanted electrons. Every bond, anytime we make a bond. So if we see carbon 4, and we always say, well, carbon 4 is bonded to oxygen, it must be the electrophile. That's a good thing to think about. That means carbon 3 would have to be the nucleophile. Right? So if I break that bond, in a retrosynthetic sense, what I would need is a negative charge there. Right? 1, 2, 3, 4, 5. And I turn this into a carbonyl because I'm already thinking, right? I know something about Grignards, and Grignards react with carbonyls to turn them into alcohols. So carbon 3 could be a Grignard. I just need to draw in MgBr, right? I could draw a Grignard like that, or I can draw a Grignard like this. It's the same. It doesn't matter. So this would be one route, that Grignard, and this aldehyde, which of course has an H here. Don't forget that. That could be one route if I broke the bond between, right, C3 and C4. Another route we could do would be to break the bond between 4 and 5. Similar idea. What's that going to look like? Well, now, it'd be this aldehyde and this Grignard. Numbering our atoms, 1, 2, 3, 4, and then 5. Be another way to do this. So another retrosynthetic problem. So you're presented with an alcohol. This is a tertiary alcohol. So I should tip you off to something that obviously this is going to come from a Grignard and a carbonyl. The problem states that. But the carbonyl is going to have to be a ketone. Now we don't know what kind of ketone, but it's going to have to be a ketone. Can't be an aldehyde. So now we need to look, again, find the atom attached to the oxygen, the electronegative atom. Oxygen pulls away electrons, so carbon 3 is delta plus, so it was the electrophile in one step before this. There's actually 3 ways you could break this apart. There's actually 3 different routes you could take for this. I'm going to do the one route, but there's actually 3 different routes. You could break between 2 and 3, between 3 and 5, and 3 and 4, right? So there's 3 different possible ketones and 3 different possible Grignards. So one I'm going to break between 2 and 3. That means carbon 2 is going to have to be my nucleophile because we're already saying carbon 3 is my electrophile because it's attached to the oxygen. So that means carbon 3, well, the Grignard would be just this, right? Again, a good numbering system, so you do not lose carbons, do not lose your carbons. Balanced thy charges, number thy atoms. What would the ketone look like? Something like this, where of course, now this is 3, 5, 4, 6, 7. So that's just one possible route. There's 3 other ways, but this is just one possible way to do this. So again, recognizing, right, where's the action taking place? Find the electronegative atoms, right? The carbons bond to those electronegative atoms are electrophilic, right? They're delta plus. So that's where the bond is probably being formed at. So carbon 2 is the nucleophile, carbon 3 is the electrophile, and that gets us to this. In the second step, we do that protonation, right? We do an addition, make a tetrahedral intermediate. Do we have any leaving groups? No. So the second step we do protonation. second step. All right, so now we have another one. So let's take a look at what we have here. We have a carboxylic acid, so a carboxylic acid, and a tertiary alcohol. It's like, all right, carboxylic acid. We haven't done much with carboxylic acids yet in class. We have done one thing, and one thing only, and that comes back to nitriles. We learned at some point, you could take this under acidic conditions, and we could turn it into the nitrile into a carboxylic acid. 1, 2, 1, 2. Right? We did learn that at some point. And so what this is requiring you to do is to recognize that in a different way. So seeing this carboxylic acid should tip you off. Well, I only know one way to do that. But also, they give you this. If you see this nitrile, that should also help you know, wait a second, what do I know about nitriles? I've only done really like one thing with nitriles, and that was to turn them into carboxylic acids with this. So if you take one step back, this carboxylic acid is actually a nitrile, right? This carboxylic acid was a nitrile. And it's even cyanide, right? In this case, it's only adding one carbon. It's a way to add one carbon to this thing. So one step back would be a tetrahedral intermediate. So draw on the stuff that isn't changing. So 6, 4, 5, 3, 2, 7, and there's 1. Right? So this was one of the nucleophiles we learned about, things that we could add to Grignards, right? We learned about, things we could add to carbonyls. We learned about Grignards. We learned about hydrides, right? We also learned about nitriles as a source, right? This K plus Cn minus, right? That cyanohydrin formation, we called it. So where does this come from? Again, you're presented with this tertiary alcohol, and the obvious place to break this, right, is between 1 and 2. And that helps to know, right, they're already telling us where the nucleophile is. So this carbon 2, again, must be where the ketone is at. So that would be the actual starting material. Let's draw it here. Number our carbons, so we didn't lose any. 2, 3, 4, 5, 6. And then, of course, our Cn minus was carbon 1. And that's where that came from. So this was the starting ketone. So we're presented with this alkene, 2-methyl, 2-pentene, and they question us and say, this needs to come from a Wittig reaction. So if we think about Wittig reactions, we think Wittig reactions have phosphorus ylids, that funny ylid thing, where we had the phosphorus with a plus charge bind to a couple things, and it was attached to a negatively charged carbon, right? We made that 4-membered ring. Yeah, something about that. But what it does, it takes a carbonyl and turns it into an alkene. So when we look at this starting material, let's number around the alkene 4. We know that the disconnection, the place we need to look at, is actually about the alkene. Right? That one side of that is a carbonyl, and the other side of that is the ylid. Right? So again, there's a new bond between 1 and 2. One of the carbons has to be the electrophile, and the other one has to be the nucleophile. Nucleophile, electrophile. Now, it doesn't matter which one we choose, right? It doesn't matter. So we have two options, right? Again, you can have the ketone or the carbonyl on either side, or the phosphorus ylid, Wittig reagent on either side. For simplicity's sake, I'm just going to choose one. I'm going to choose to have carbon 1 have the ketone. That means carbon 2 needs to be the one that's attached to the phosphorus. But carbon 2 also needs to be attached to two, 3, 4. Right? Oops. So this would be my two reagents. Carbon 1 is my electrophile. Carbon 2 is my nucleophile. And you can see me adding that 3-carbon piece. This is my Wittig reagent, right, to make this work. So again, similar problem that we've seen before. Presented with an alcohol. It's a secondary alcohol, meaning that it had to come from an aldehyde. And they're telling us which aldehyde. They're saying acetaldehyde, which is this aldehyde. Acetal means 2-carbon piece. Acetaldehyde. So because they're telling us which aldehyde we have to use, that is not giving us the freedom to choose which bond we want to break here. We know carbon 4 is going to be the electrophile, either way. But they're saying this 2-carbon piece, so I got to go this way to break this bond. So I'm breaking between 3 and 4. So one step back, what would the Grignard have been? The Grignard would be an ethyl Grignard, methyl ethyl propyl. Again, classic things people will do. They won't number their carbons and they'll lose the 3rd carbon. They won't show that bend there for the Grignard being there. Then they're asking us to go one step back again. How do you actually make Grignards? Where do Grignards come from? Right? Remember, Grignards come from alkyl halides. Again, so that would be from an alkyl bromide. So bromopropane. Propane. Propyl Grignard. Oh my goodness. Methyl ethyl propyl. 3-carbon piece, propane. Propyl Grignard. Bromopropane. Yes. Right? Will get us there. Right? So we have to get to that. Change carbon 3 from an electrophile to a nucleophile. Well, then it can react with the electrophile carbon 4. Makes a tetrahedral intermediate. Tetrahedral intermediate. Are there any leaving groups? No. Protonation. Alcohol. Done. So this one, not a retrosynthetic problem, more like a forward problem. You just got to know, essentially, do you know your reagents and how they work? You could make it a retrosynthetic problem if you want to. You could work backwards. If they hadn't given you this, you could work backwards. But at the end of the day, hopefully you recognize 1, 2, 3, 1, 2, 3. So you get propane. What would this have came from? Maybe it's kind of hard to see. Now the key, though, is to recognize this HBr and peroxides. So that radical reaction we did before where we get that anti-Markovnikov product. So this is kind of something you just kind of got to know. Right? Some of these things you just got to know. That when you have this, when you have these reagents, you get the bromine to add to the less substituted carbon. Right? The less substituted carbon. Not gonna go, you don't need to know the mechanism right now, but you need to know that. And so once it goes to less substituted carbon, we then would make a Grignard reagent, right? Just like we've done previously. 1, 2, 3. And now here's the kind of thing we always forget. A Grignard reagent, right, reacting with water, what's that going to make? Right? What's going to happen there? Well, it's just going to be a deprotonation, right? So if the Grignard, right, if it's C minus here, and that C's water, what's it going to do? Well, it's just going to act like a base. It's going to act like a base and take that hydrogen, and you're just going to make propane. So carbon 3 here, right? Carbon 3 has how many hydrogens on it? It always had 2. And that didn't change until all of a sudden at the end, carbon 3 has 3 hydrogens. So where did that hydrogen come from? From the deprotonation of water. That's how you get to this type thing. So again, radical reactions using Grignards, right? How do Grignards react? So kind of combining 3 different concepts and ideas. All right, so here you have an example, retrosynthetic problem. So we're working backwards from this cyanide to this benzaldehyde. So one of the things you should recognize right away, if I just number 1, 2. 2. I added a carbon, right? I had to add a carbon here. Now, how did I do that, right? How did I add a carbon to this position? I obviously added a carbon here that wasn't there before, right? And you've seen this where adding nitrile is a good way to add 1 carbon piece to a carbon of the carbonyl, right? This could be a nucleophile, right? Cn minus, and this could be an electrophile. So we kind of have an idea where we need to go. but it's going to take a couple steps to get there. Okay, so the first thing we need to think about here is a little different. So this is a retrosynthetic arrow. That's a retrosynthetic arrow. Notice how there's no alcohol left, right? Like, that's a little weird, right? There's no oxygen left, I'd say. So we need to have, we already maybe know that this is the case, right? Cn minus is there. So that's carbon 1. But I don't want to do an addition. I don't want to add to a carbonyl, because if I add to a carbonyl, I'd have an alcohol here, right? But I don't have an alcohol. I just want to do a straight up substitution. What if I had something here that was a good leaving group, right? So I'm thinking like SN2 style, right? Something like an SN2. What are things that are good leaving groups? Bromines, right? Bromines, activated alcohols. Remember those 5 ways? Oh gosh. Didn't you learn 4 ways to activate alcohols and make them into good leaving groups? You did. Oh God. Oh golly. Golly gee willikers, as my mom would like to say. So this is kind of, we don't need to really think about this guy. That's there. Okay, we can add that in. KCN, fine. What could 2 have been? Well, 2 could have been an alcohol, right? Or it could have had an alcohol on it. Because we're calling for it to become a good leaving group. But before we did that, it could have been an alcohol. Because we know ways to activate alcohols and turn them into good leaving groups. Now I have this alcohol, a primary alcohol. Do I know a way to make an aldehyde into a primary alcohol? You do. You maybe don't remember, but you do. There's a way to do that, right? So let's do the forward direction. Let's come forward now. So what is the reaction that we're doing here? What are we doing? Let me help. What are we doing to carbon 2? We're adding hydrogens to it and getting less bonds to oxygen. We're doing a reduction. How many ways do you know how to do reductions? Well, maybe 3. Sodium borohydride, lithium aluminum hydride, and dibol H. And dibol was very specific for esters. So let's do sodium borohydride, right? Awesome. Sodium borohydride. Great. Now we need to activate this alcohol. So we know a bunch of ways to do this, right? Pick your favorite one, right? We knew the zinc chloride HCl. We knew SOCl2, right? We know the mesylate and tosylates, right? And then, of course, we also know good old PBr3, right? PBr3 in that pyridine. Again, not asking you the mechanism, but remember those reagents, how to do these things. That would turn this OH, right, into what? It would actually turn it into a bromine. And then we can easily do an SN2. And that gets us to this final product.